Okay, so we had quite a few slides this morning talking about interconnect verification, either as a challenge or as one of the main aspects that really needs to be cared of at system level. So here is a presentation of what we provide as part of a more complete solution. So I'm going to give some technical details about what we mean by the Interconnect Verification Challenge. I'm going to present also a generic scoreboard to address these kind of issues. So what I mean by interconnect is this yellow cloud, and I made it a cloud because it is a cloud in the sense that there are many, many features. So the interconnect is no longer just a bus where one master sends a transaction to one slave and this is it. There are many more than that. We talked about cache coherency, but there is just more. The interconnect first can talk with master and slaves of many different protocols. So we need to deal with not only AMBA bus, but also probably OCP, or you may get some internal corporate bus protocols. You may take wishbone bus if you reuse some open core IPs. There are many different buses you can deal with. You have different bus sizes, you have the memory maps, all are the main characteristics of your interconnect. But on top of that, then you have your SOC-specific features. We now have virtual address space at system level, so it's no longer just one physical address. We have virtual address space. We have the cache coherency, which breaks a bit the concepts we had before. The SOC can be completely reconfigured. The address space can be reconfigured. We need to deal with security. Some slaves, some memories can be secured or not. This is completely reconfigurable. You may have different level of securities. These are SOC specific. We need to deal with the error management. Invalid requests should be responded with an error, so that the software can actually deal with an interrupt or whatever. We also need to deal with power management within the interconnect. The interconnect needs to be aware that an IP is off, so that at SOC level, we've got the right interrupt or the right messaging going back to the CPU saying, hey, you're actually trying to read a memory which is off, so what action should I take from here? So the interconnect now has this kind of feature to tell the CPU you're doing something wrong. In terms of the verification plan of the interconnect, it's strongly related to the previous slide of the characteristics. The main point is about verifying the address map. This could be quite easily automated. Protocol sanity could be also kind of automated with either random or just a for loop, going through different kind of transactions. But what we need to care about is all these SOC features where it's not that easy to automate, in the sense that for each SOC it will be different. And for each customer, you may actually use different setup of security could mean different things. We also need to care about the cache coherency. We need to care about the power management. We had a slide, I think that was from Mark, talking about the performances. The point of the interconnect is to route transactions, but it needs to route it with a specific latency from one slave to a specific from one master to one specific slave, so that the CPU can actually do real-time software, or a video engine should have enough bandwidth to actually run. So performance is also one important aspect of the interconnect verification. The But not only the interconnect needs to work, it also needs to work once integrated in the stock into the system level. So we need to verify the interconnect, the integration of the interconnect. And also use cases, we need to be sure that actually we can run the video in the same time as the audio, for instance. Basic things first, routes on address map, we need to be sure that all masters can access all slaves that are specified to be reachable. Nothing complicated on that. What's complicated here is the numbers of masters and slaves, which are now reaching over 50 masters and 70, 80 slaves, depending on which SoC you're working on. So it could lead to a few hundred possible routes in the end. Protocol conversion issues. So if one master is responsible to send one transaction to one slave, this is fine. It means we carry a message. The message is usually specific data to a specific address. Now, if you look at one simple AXI transaction here, the request here is burst of length 3, starting at address 5. We're doing a load, nothing complicated. So we're going to read the address 5 up to 17 in XML. These are the data that we care about. Now, if you convert this to the slave protocol, it could lead to some funny realignment where actually the interconnect will issue 2 transactions because we're in a different protocol. There is no equivalent of the AXI burst and the realignment of the address, and you'll get actually a read starting at the address 0. There's some stuff that could happen. So when you verify an interconnect, you need to care of it. Now, if you have same protocol, but in 32-bit interface, you may have the same 2 transfer realigned at the address 0. This is fine. We just read more data. There's no big deal. But some designer might be clever and say, oh, in this case, I'm actually not issuing this first transfer. So I'm actually starting at address 4. As a verifier of the interconnect, you cannot predict what the interconnect will do for you when you have such transaction. And you still need to care about the address 5 up to 17. These are the data that you need to verify. So in terms of Testbench requirements, when you verify the interconnect, first you need all the verification IPs of the different protocols so that you can verify the interconnect interfaces. Obviously, the verification IPs needs to have everything in place, monitors and checkers of good quality so that you be sure that you cover everything. You need a virtual sequence on top of all verification IPs so that you can control them once against another one. So you can synchronize transactions from different masters. But you also need a scoreboard which is able to deal with all the different masters, all the different protocols, all the different routes. This scoreboard will do the end-to-end transaction. It needs to care about the protocol conversion that might provide some issues, and it also needs to deal with all the SoC features, including the cache coherency, the power management, the security, the attributes of the transactions. The interconnect could be verified as a standalone block or within the SoC. At standalone, we can verify the interconnect as soon as it is delivered. In some companies, the interconnect is generated within a few hours, so we can start verifying it very early. But if you verify the interconnect in standalone mode, you can't really check the interaction of the interconnect with the actual IPs if all the signals are properly connected. Some designers may have made some wrong assumptions when they integrate. And if this is the case, your SoC might work with a non-stressed test from the CPU, but it might break because the ground is always 1, stuff like this. So standalone, that's the kind of easy part, which is connecting directly the verification IPs to the different interfaces, connecting the scoreboard to the different verification IPs, configuring it. Some have written script to automate this part. This is automatable. And you can get out of the box automatic checking of all the routes. Verifying the interconnect at SoC level. So you're reusing same configuration of your verification environment, but the difference is that you're now using the real SoC instance. The only thing is you replace all the different IPs to be a black box, and you control the interface from inside the verification, the IPs with the verification IPs connected to the interface of the IP. So going a bit more in details about the scoreboard itself. So the scoreboard should be able to be connectable to any protocol verification IP. It needs to check transactions from end to end, from master to slave. For this, it needs to check not only the data, but also the directions, read or write, the attributes. So we've got all the, if we look at the AMBA specifications, we've got all the cacheability, protection modes, all this stuff. The scoreboard should handle this. The scoreboard should be able to check the response code. So if we get an error from the slave, we should be able to check that the master gets it. The atomicity, so if a burst should not be broken, the scoreboard should handle this kind of thing. But it should also support multiple address maps. So you could have a shared memory map for your entire system, but you could also have different CPUs having the same memory at the different addresses from different point of view. The address map could be reconfigurable from different masters. The scoreboard should be able to handle the security and power management and the cache coherency features. And some more user-specific features like DRM, digital right management, stuff like this. So because of this, we came up with an architecture of scoreboard for SoC, which has actually some settings. You can say, okay, all AMBA, for instance, or all AXI, so I'm going to use a strict comparison. There is no way I can get extra reads, as shown in a previous slide, or because I have many different protocols, there is no way I can say if there is extra reads or not. So I'm going to set the scoreboard in a more permissive way. The only thing I care about is that the right data goes at the right place. If you look at the UVM manual or a UVM tutorial, you will get some quick introduction how to build a scoreboard between two monitors. Mainly these tutorials are talking about scoreboards using the same protocol on both ends, so with no real issue there. You don't get any information how to build a scoreboard to deal with all the security attributes and all this stuff, or address alignment. So the scoreboard structure we came up with is a scoreboard with an internal generic transaction so that we can plug it to any kind of verification IPs. We can extend it using the attributes. These generic transactions are translated between the monitor of the verification IP and the scoreboard are translated using adapters. And this is the bus specific part of the scoreboard. To some extent, inside there is one simple scoreboard per route, one master to one slave. The address map is completely reconfigurable. And here is a picture of the scoreboard architecture we came up with. So we see here that the monitors, between the monitors and the master interface of the scoreboard, we've got the adapters, which does the transaction of the HB, if we look at the first one, into the generic bus transaction. And then the scoreboard is able to do everything internally. Then when we talk about cache coherency and ACE, for instance, the issue with ACE or cache coherency in general is that it just breaks everything, all the principles you had when you say, I've got an address, my transaction should go to this slave. The cache coherency just breaks it in the sense that I've got an address, now I'm going to talk to the other caches. Do you have this address as well? One might respond, yes, I have the data of that address. So the address, the transaction will not go to the end memory. It will go actually to the other cache, which will respond to it with the appropriate data. So it just breaks everything. So what we came up with is that we use actually the same structure, but we add an extra layer, which is the ACE or cache coherency scoreboard to deal with this. And if the transaction was related to a cache coherency, it will go first into the scoreboard, the cache coherency scoreboard, before going to the rest of the different routes. So just one slide to show the path of one transaction from the monitor to the adapter, then from the adapter to the scoreboard master interface. Then it goes into the appropriate path inside the scoreboard, and this is where the check is really done. And then get back. On the slave interface, we got the same thing. The transaction is first translated by the adapter, then goes into the scoreboard interface in its generic form. Just to give you an example how to use it, so you first instantiate it, give it a name, you define the different address domains, you define for each address domains the different segments. So we got 3 slaves defined here at different addresses. For the other address domains, you define some other addresses. You then declare your CPU, your masters, you declare your slaves, and then you say, okay, this master can talk to this slave, and I connect the different adapters to the actual monitors. Okay, so about the advanced features, then if we talk about the protocol conversions, it's internally handled by the way we interact with the adapters. The dynamic address map is supported using an API to reconfigure the address map. The attributes, so we provide support for the AXI attributes. Now, if you want to deal with your own attributes, you can always use the UVM factory to replace a class by another one. The security and power management, so because it's an SOC feature, we cannot predict exactly what you will put in there. So we provide some user-defined methods that you need to overwrite and put your own code. Functional coverage, so all the basic is provided. ACE and cache coherency, so there is one support for the ACE transactions. Now, if you have something which is different, we probably need to adapt and override the different methods using the factory. In all cases, there are virtual methods in the classes, and you can always use the UVM factory to create your own features on top of it. So I've personally used this kind of methodologies on 3 different projects with approximately 40 masters, 60 slaves, and about 200 different paths, with 5 different protocols, 3 batch sizes, power management security, dynamic addresses. I found out that developing the scoreboard, I first said to the project manager, oh, this is just a scoreboard. Let's take the UVM manual. And then it turned out that it was a project within the project. Having the right scoreboard architecture is actually key, especially if you then think about the next project, which will be a different interconnect. In terms of verification results, we found address map issues, wrong protocol translations on some fixed addressing mode. We also found some deadlock related to the power management. Actually, the transaction which was blocking because of the power management was actually blocking the transactions to wake up the IP. So there was a deadlock like this. To summarize, so I actually have 2 summaries, one on the interconnect verification and one on the scoreboard. On the interconnect needs to be verified from master to slaves, but at SOC level if you really want to be complete in terms of integration. We need to verify the interconnect with complex scenarios, with stress and congestion conditions to actually make the arbiters switching, and having the right interconnect scoreboard is a key to actually be sure that the interconnect works properly. And for the scoreboard, having one which is generic and configurable really saves you time for the following projects. It should be compatible with any kind of verification IPs. So if tomorrow your manager say, oh, by the way, there's a new protocol, can we support it? You can say just, oh, yes, give me a day. It should allow the verification of the SOC feature, which is actually a challenge because the SOC features are all different for all SOCs. So we need placeholders, we need the right patterns to actually put your own code in it. Any question?
Yeah, Jerome Momal from Samsung. Yes, you mentioned performance verification as part of the scoreboard features. Can you elaborate a little bit? For instance, when it comes to the performance verification, usually the 2 usual keywords are bandwidth and latency, but these are very vague terminologies, right? And for bandwidth, just verifying that having 10 gigabytes per second transfer on a given size doesn't guarantee that you will have this bandwidth for any size at any time, depending on the rest of the chip operating in different modes. The same goes for latency. Yes, you can very easily check that for a few accesses the latency is as expected, but under very heavy stress you can spot that the maximum latency is actually much worse than so you expect.
The scoreboard has all the information of a transaction going all the path from the master to the slave and then get back to the master. So it can record all the timing, all the information that are required for the performance analysis. Now the scoreboard is just a scoreboard. it will just report the latency or the bandwidth depending on the traffic that you have generated. So if you really want then to use this to do proper performance analysis, you need to work on your test scenarios to have the right set of tests that will exercise your design in same kind of use case that you're marketing and solve it to your customers.
Okay, thank you.
That's another question.
Yeah. Okay, my name is Inan from San Sirion, Switzerland. I have actually two questions. The first one is from standalone to testbench and headless context. The difference I see that the VIPs are there, I mean the monitors and the drivers, but also the RTL blocks are also there. So what's the idea of having such a setup? If you have an RTL in and still the driver and the verification part, what is the functionality of RTL in that?
So one point is the difference should be nothing. Now in practice, the difference is that you actually verify same configuration, same architecture, but from the IP interface to the IP interface, rather than to the scoreboard interface to the scoreboard interface. So you actually verify the interactions that you may have here. So you may have clock domain crossing, you may have power isolations, you may have this kind of thing where it's easy to add bugs.
Okay, I have a practical questions about this again. Are you like kind of forcing all the interface at RTL levels so that there is no traffic generated by the RTL itself?
Yeah, there are different ways you could do it. One is just reusing only the interface, and you play with VHDL configurations, for instance, to replace with the black box. The other one is to actually force. There are different ways you could do it.
Okay, the second question is the end-to-end scoreboard. So from your experience, is it better to have this end-to-end scoreboard with all these address map changes, etc., or is it more, let's say, will it make sense to have local scoreboards and then tying them together at the end?
Well, it's so the presentation from Jerome actually made this point that he wants to reuse IP stuff, IP verification at SoC level. It could save you time. Now, if you look at the SoC level, you need the vision of what the interconnect is at this level of abstraction. If you just connect things together, you're just rebuilding the interconnect as a design. So you don't have the same level of abstraction. You don't really, it's difficult to say, yes, I'm building something which will verify what the intent is.
But that causes a redundancy in the work. I mean, if you have like something in place at IP level already, which is verifying these address changes, then you have to reinvent this time to really.
It might or not. It will not, because I mean, if you're using smaller scoreboards and then plug them all together, I don't believe you will get one which will actually deal with all the routes of the interconnect.
Okay. Okay. Thank you, François.